So this is, I think, the second presentation, right, of the PACBIC.
Third one was in Riverside, and then
okay.
we had the other one here.
Okay,
Yeah.
well, so this is anyway part of that presentation series. And I'm the PI to one of the objectives, which is aim number 1A, which has its title a very narrow scope, where we're trying to predict the efficacy of field adulticiding from bottle bioassay and KDR frequency data that we get from bottle bioassays, and also from genotyping mosquitoes, individual mosquitoes. It's much easier said than done. And I'm hoping that at the end of this presentation, we'll get some perspective of how complex this is and how many variables there are. And it's a 4-year project, so hopefully we're going to be able to have time to still just scratch the surface, but nevertheless answer some important operational questions. Of course, none of this work that I can present now, which was done over the last 5 or 6 years on an ad hoc basis when districts required it, were done with collaborators mainly from the Consolidated Mosquito Abatement District, which is the district that's just near to my lab. Fortunately, they're a very research savvy district, so they are happy to do research with me. There are districts in California that are unfortunately not research positive, so it's sometimes difficult to do research in some parts of California. Then a lot of this work I have to the contributions made by Dennis Candido, who works for ADAPCO, who helps supply the chemicals, formulations that we use in the field trials, and he also helps with the fogger calibration to make sure that the amount that comes out of the truck is the amount that's supposed to. And then Yusuf and Catherine Briscoe, who work with me in the vector genetics, who help with the data analysis and genetics and so on. So it involves quite a few people, and I'm hoping that once I've had one season where I could focus on answering this question, we'll have involved other districts as well. So basically the premise for this question is, can we predict expected control that from bottle bioassay data? And there are several reasons for asking this question. The first is that despite the fact that we've had many, many years of doing bottle bioassay data and doing bioassays in the lab, no one's never made that connection between what we see in the lab to what we can actually expect control-wise. So that question has never been answered satisfactorily enough, and the CDC would like this answer because it helps with making recommendations about whether to spray or not to spray, and where to spray and how to spray, and is it worth spraying, is it worth the costs of spraying in terms of disease reduction and so on. So there's a very operational component to asking this question. This justifies then doing insecticide resistance monitoring. If we can't draw any conclusion from bottle bioassays, then why should we do it? We're wasting our time. So I'm going with the hypothesis that we can. And hopefully in the next 4 years we'll answer that question. Then, if predictions are possible, then can I provide appropriate recommendations to the control districts? You asked me questions about, well, you've done bottle bioassays, you've done genotyping of the mosquitoes in my district, so is it worthwhile spraying? And what do I spray with? And to be perfectly frank, I can't advise them appropriately currently. There's also, what makes things very difficult is there's no homogeneity in the bioassay results spatially. So I can't just take a mosquito from one location in California, get an answer, and advise all the districts throughout California, because it's just too much heterogeneity. So we have to do resistance testing on multiple populations and multiple times of year to really get an appropriate answer. And then what complicates things even more is the fact that we're never dealing with just one resistance mechanism. There's many things occurring parallel with each other, and the science behind identifying the resistance mechanisms in mosquito work, while it appears to be advanced, a lot of people have done work on this over the years. It's still, our understanding of resistance mechanisms, in my perspective anyway, is extremely poor in mosquitoes. A lot of work needs to be done there still. So just to get back to point D, and this one is particularly relevant here. And this just shows you how, so these are model bioassay results where we look at knockdown to the presence of permethrin in Culex pipiens populations in California. And if we just focus on this block here, you can see, and each one of these square blocks is about 1/4 of a square mile. You can see how much heterogeneity there is in knockdown, even on a small spatial scale like this. And you can't necessarily make that assumption that where there's extensive use of pyrethroids, one would expect the populations to be most resistant. This is mainly agricultural use of pesticides. The amount of pesticides that we use in mosquito abatement is actually extremely small compared to what's used out there in the agricultural industry. But nevertheless, mosquitoes that are breeding in the vicinity of the crops that they spray still get exposed to these chemicals. So spatially, there's tremendous heterogeneity. And the reasons for that, of course, would be related to the genetics of the mosquitoes and, of course, the mechanisms that confer resistance or conversely susceptibility. Culex tarsatus, on the other hand, which is another vector species, obviously in California, of interest because of its vector West Nile and various other viruses, appears to be far more uniform with respect to its knockdown responses to pyrethroids. And that maybe makes sense since there's never been real strong evidence that there's population structure within Culex tarsatus in California. But there definitely is population structure within the Pipiens complex, which we don't understand quite fully yet. And then what we thought would be nice was we examined the genotype of 13 specimens of Aedes aegypti from a location in Clovis and Madeira, and all of them showed homogeneity with respect to a single mutation that confers sensitivity to pyrethroids. So we thought, you know, maybe there was a single introduction of Aedes aegypti that brought in with us this nice homogeneous voltage-gated sodium channel gene sequence, and so maybe resistance-wise, they might be homogeneous. But of course, that's not reality. Never is. And with work that Yusuf has done, where we've compared the single nucleotide polymorphisms across the genome of multiple populations of Aedes aegypti from throughout California, they essentially cluster into 3 genetic groups. So those from Southern California are actually genetically quite different from those that we find in the northern, all northern populations. And even in the northern populations, where we look at Madeira, which is in the blue, they're quite different from what we see in Clovis. And then here, it appears to be more admixture of populations. So really what this suggests 2 things. Is that there's likely to have been multiple introductions of Aedes aegypti into California. It's not just spread from one single population that entered somewhere and spread throughout California. Rather, it's been multiple introductions. And now that we know that we're dealing with different genetic backgrounds, we're probably also dealing with different resistance mechanisms, not just a single kind. So this complicates interpretations of bioassay or insecticide resistance considerably. And so you have to take the genetic backgrounds into consideration. The other thing that's also occurring, which is quite interesting, is that if we compare just the Clovis individuals from 2013 to 2016, and we compare the SNP profiles across the genome, it appears that there are certain portions of the genome between 2013 and 16 that are undergoing very strong selection. So what's genetically apparent now may not be genetically the same in several years' time because these mosquitoes are apparently undergoing some kind of adaptive selection. And it's occurring in several parts of the genome. And it will be interesting, of course, for us to look at what genes specifically are within these parts of the genome that show appearance of selection. There may be genes are involved in resistance, we don't know. There may be genes are involved in drought tolerance, because we never expected these mosquitoes to survive as efficiently as they have in California. We have very hot summers, and these mosquitoes are active during the day when it's well over 100 degrees. But it may also be a selection for overwintering, because in Clovis, we do get several weeks of below freezing temperatures. And so there may be some adaptations occurring with respect to overwintering. Maybe the eggs can survive lower temperatures for longer than typical temperate populations. There may be, well, there could be a number of ways in which they could be overwintering, and right now we don't know how these mosquitoes are overwintering. We suspect they're overwintering as eggs.
Anton?
Yes.
Is it possible that you could get multiple introductions to Clovis? So like after 2013,
Yes.
that you get a new population coming in, or is it just select? And that, how would that affect the patterns you see here?
Well, sure, that, yes, we can't necessarily exclude that possibility. I mean, the burning question for me is, we've had 100 years of Egyptia occurring on the East Coast. Okay. And for 100 years, it's had opportunity to enter California and never established itself. So suddenly in 2013, it establishes itself in 3 separate populations. So what happened? And it would possibly be interesting to see if there were some kind of combination of genes that were expressed that allowed these mosquitoes to suddenly have that ability to survive in this environment. But the fact that we've got kind of proof that there've been multiple introductions in different parts of California, we can include the possibility that there's multiple introductions still occurring in these parts of California. Sure, so we have to take that into consideration. And this is a very old slide, but it still tells a story that I think is very relevant, and that is, if you look at esterase expression patterns of Culex pipiens complex members, they're also not consistent from one location to another. So here from Clovis, for instance, the pipiens have expression of a lot of esterases. And esterases supposedly sequester organophosphates to confer resistance to organophosphates. But then if we look at a population from Marin, they have very low expression of these esterases that supposedly sequester organophosphates. So they're quite heterogeneous. And this essentially occurs even at a smaller scale, where I've actually looked at individuals from within Clovis and the subvariability. And so that has allowed us to consider the possibility that if you want a resistance breaking strategy, we can use mosaics of formulations. You switch between pyrethroids and organophosphates, or you can use mixture. You can actually purchase a mixture that has both a pyrethroid and an organophosphate in it, which I only propose that districts use in case of emergency to make sure that they knock out the resistant population. And the other interesting thing here is that individuals that have this high esterase expression pattern are resistant to OPs, but they're susceptible to pyrethroids, and vice versa. Those that are resistant to pyrethroids don't appear to have this very strong esterase expression pattern. So resistance to these chemicals is occurring at a cost. And so there's a balancing act that the organism is faced with in the environment.
Yes. Is part of the theory, you probably already said this, that you said that the agriculture uses so much more chemicals
Yes.
than mosquito workers. And there's a lot more, I think, agriculture in the Clovis area than there would be in Marin. They use OPUs.
The districts don't generally.
No, but
use
what about the
OPs.
farmers?
Well, farmers do use some OPs.
Okay.
Yes, they do. But OPs were used, household use of OPs were used a lot until about maybe 5 or 6 years ago. Now it's hard to find an OP product for sale at Home Depot or Lowe's. It's all pyrethroid based.
For like cockroaches and stuff, ants?
Yes,
Yeah.
that's right. Yeah. There's a lot of household use of these chemicals as well.
Okay.
I mean, I see the pest control agencies every day going down my road to someone's house. And these run off. So let's just get to, that's a bit of background. So now, some of the URV methods that we apply here. Generally, it's accepted that aerial spraying should take place when the mosquitoes are active. They're actually actively flying, not hiding away under the trees and in the structures. So we're always looking for appropriate meteorological conditions when to and Cupid's Pipiens anyway are most active just before sunset and just after sunset. And that coincides with when we have the strongest inversions. So in other words, the temperature low down on the ground is colder than the temperatures higher up. And so it essentially traps the pesticide down for a little bit longer, rather than the pesticide just immediately floating up into the air. And it also has to coincide with periods when we have least wind, because the spray, you don't want the spray to go too fast, and you don't want it to have no wind where it just doesn't spray at all. So once again, it's a balancing act between the wind direction and the amount of wind and the temperature. So that appears to be coincident with the Culex pipiens activity. Unfortunately, that period when we have this inversion is not coincident with Aedes aegypti is most active. Most Aedes aegypti are most active about 1 or 2 hours before sunset. And then when the sun, when the sun goes down, the Aedes generally reduce their activity. So in the UR methods, what we do is we place mosquitoes opposite the direction of the wind to try, and we place about 20 mosquitoes in each one of these cages, and we place these cages at specific distances away from the spray source. And in these cages, we place both the test population, so mosquitoes that come from where we collected them in the wild that we want to test for resistance to, and then we also have susceptible control mosquitoes as well. And in some instances, we've also had opportunity or access to these, what we call spinners, which is a little device that has these 2 slides here on it, and this spins, and as it spins, it captures droplets of the formulation. So we can actually look at the slide under a microscope, count the number of drops, and count the size of the drops to try and associate the amount of chemical to mortality that we see in the sample cages.
Okay.
Realize? Okay. Yeah.
It is easy. Is this something you kind of invented, or is this a standard technique that people use everywhere?
This is a kind of standard way of doing URV trials, which is not perfect.
Okay.
The design of the sentinel cage, people use different designs there, but generally people do follow this protocol of 50 feet, 100 feet, 200 feet, and they don't expect chemicals when sprayed from a truck to travel much further than 300 feet. So that's why you put the last sentinel cage at about 300 feet, which is 91 meters. So this is in an open situation here, where we do most of our trials, which is not appropriate, because mosquitoes are not found in the open like that. They're found in urban situations. And to get permission for us to do ULV trials in urban situations is a lot more difficult. But that's why I work with the districts. And so we're hoping that in the next 4 years, we're going to do a lot more trials in urban environments. So after we've sprayed, we leave the mosquitoes in these sentinel cages for an hour. And then before placing them in the truck to take back, a 1 hour knockdown measurement. Then I place the cage itself into a plastic bag, a Ziploc bag, give it a bit of sugar water, and then hold the cage for another 12 hours and another mortality after 12 hours. So we've done through the years on an ad hoc basis, I've done some ULV trials. And so I'm trying to draw some initial conclusions from the results of these trials without necessarily starting specifically answering this aim. The bottle bioassay methods that I use essentially follow that's recommended by CDC and WHO. They follow the same protocol, so that's good. And I place about 15 test mosquitoes in each of 6 bottles that are coated inside with the technical grade insecticide. Then I also place 15 susceptible mosquitoes in each of 3 bottles as a control. And then I also place 15 test and 15 susceptible mosquitoes in bottles that are coated just with acetone, because the technical grade formulation is mixed with acetone, so it evenly coats the inside of the bottle. And you always want to make sure that that mosquitoes are not dying from acetone, which is not the insecticide. So it's just essentially a control. Wherever possible, I do the bottle bioassays on F1 generation. So I collect wild individuals, get eggs from those, and then test their offspring. I don't like testing mosquitoes on colony material for 2 reasons. First is they very quickly undergo genetic bottlenecking. So the heterogeneity in colony material does not really reflect heterogeneity in the field. And very often, the resistance mechanisms that you can select for in the lab are not those that evolve in the field. So you don't want to create something that's not real. You'd rather test these on actual field populations as best as possible. And then I always obviously generate more mosquitoes than I need just for the bottle bioassays. I then have enough from that generation available for me to put. So I'm really setting. So it gives some insights into how we're looking at this data. And Yusuf helped me with this aspect. So in general, there's not much difference between knockdown time at the 12 hours versus what knockdown that I see after 1 hour. And I'm interested in answering that question because I'm always trying to save time, trying to save effort. And the moment you put a mosquito in a cage, the mosquito knows it's in an unnatural environment. So it's immediately under stress. So it's always trying to separate the death due to stress versus death actually due to the insecticide. So the less you handle these mosquitoes, the better. And so that's why it would be nice if I could just stop the assay at 1 hour and not bother about holding it for 12 hours. So we're just looking in to see if this is a possibility. And so we've looked at various chemicals here, and of course CQ1 stands for Culex squink susceptible population. These are susceptible Aedes populations, and then these are the actual field test populations. And in general, the number of mosquitoes that are knocked down in 12 hours are much the same as what we see in 12 hours, except for malathion and Culex pipiens populations. So it's not going to work apparently for organophosphates, but it may work with pyrophores. With Aedes, they're not really significantly different, even with malathion. So different mosquito species will respond differently to chemicals. Then we also looked at URV application efficacy at various distances. So do I have to place traps or sentinel cages at all these distances? Maybe I can get by with just putting it at one distance and put more replicates at a single distance rather than setting up all these lines. And certainly with susceptible strains, there is really very little drop-off in death from 15 to 91. With the wild populations, certainly with permethrin and PBO, there's not much drop-off in the first up to 200 feet, but then there is when you go to 300 feet. And I must say that these results, except for this year, was all based on open trials. We have to do all of this again with more replicates in urban trials. But you see, but I put this in here just to bring home a point. That when you go into an urban situation, you have much more variability with respect to mortality in sentinel cages. It's distances away from risk racers. And that's because you've got walls, you've got houses, and you've got trees. And all of this interferes with the movement of the insecticide penetration. So this is a very, very important aspect to look at further down the line, because CDC is not really interested to know what control we get in open trials. They want to know what control we're going to get in urban situations with the diseases.
Interestingly, the distance is not affecting efficacy in urban conditions, right?
Yeah.
So it's not changing too much between 15 meters and 91 meters.
Yeah.
How do you explain that?
Well, the few urban trials that I've done, the results between each of the trials have been quite different. And I haven't really been able to draw, and this is based on very few replicates. So it's a very small sample size, which is problematic. Because we just haven't done enough. But it's all this swirling of the insecticide that happens that just creates different results from one trial to the next.
Can be
And it's hard to draw those conclusions.
Can be a positive results if distance is not affecting the efficacy at all.
Yeah, if you look, if you look at this is considerably lower than at 91. So there may have been a shadow effect at the house, because this is the front of the house. This would be more or less middle of the house, next to the house. Then this would be going behind the house. Then this would be going in the backyard of the house next door. And so there's all these shadow effects that may be happening and swirling. So we're going to have to do a lot more trials. But yeah, sure. If I can get away with putting a cage just at one distance, I'd be very happy to do it. Because you have to get the owners to agree to being present there, putting up all these cages, and you want to be as unobtrusive as possible. So in some instances, distance really doesn't seem to affect death with susceptible strains, but it does start having an effect on the wild populations. And that's because there is resistance. And so this is probably going to be a dose-dependent factor. That further away it's from the source, the less chemical there's going to be. But realizing that putting a mosquito in a sentinel cage is not the real thing, because you're forcing them in a cage. And in the wild, when they detect a chemical, the very first thing they might do is fly away. And so they just, don't get exposed to it like they would in the sentinel cage. So these are caveats of this whole study that we have to think about. Someone wanted to ask something. Oh. And just because a mosquito is necessarily resistant to one pyrethroid doesn't mean to say it's going to be resistant to another pyrethroid or organophosphate. So, for instance, here's an example where these Clovis mosquitoes are quite resistant to permethrin and PBO. They're more or less just as resistant to pyranose, which is a different pyrethroid, but they are quite susceptible to deltamethrin, which is also a pyrethroid. And what I do want to say here about ETO, which is also a pyrethroid, fenprox. Fenprox, it's never a good chemical to do bottle bioassay with because it crystallizes and it never forms a nice smooth coating inside the bottle. So you're always going to get wacky results with fenprox, which is registered for use in California. So we do get different responses to different chemicals. And then to get to the crux of answering this question, and this is based on a very, very small sample size because the study is only, it hasn't really started because I only got the model recently, and this is the first year we're going to do it. But this is based on the few assays that we've done. And Yusuf looked at all the different combinations of looking at different distances, looking at different concentrations of chemicals, and looking at different knockdown times that we observe in the bottle bioassays. And the best correlation that she found, certainly with pyrethroids, was that mortality at the 12-hour period showed best correlation with knockdown in the 2-hour period in the bottle bioassay. So this may be something that we hypothesize now, that we can hypothesize now. If we look at the knockdown time to pyrethroid at the 2-hour mark, that would compare to what you observe in a URV trial, 12-hour mortality. So if a district calls me up and I'd say, well, in an open situation, that's what you would expect. But coming back to this, see, if you apply a chemical in an open trial at these distances, you get high mortality. And in a moment, you apply these chemicals in environments where there's interference in the movement of the insecticide. So in corn, you see a dramatic drop in mortality in the sentinel cages. Further away you go from the spray source. And then in an orchard, it was even worse. This is a citrus orchard. There's almost absolutely no death in the sentinel cages. And that's where the mosquitoes are resting. That's where they are, in the shade, because they're trying to get away from the sun. And it's hot. So all that work that I've done on the open trial, how does that relate to what we see in situations where the mosquitoes are actually present? Then, of course, ultimate goal for CDC is to give them recommendations as to, well, how much effect of disease reduction are you going to have if you spray or don't spray? And of course, one way of doing that, of course, is looking at how the spraying affected mosquito abundance in this case, in CO2 beta CDC traps and the gravity traps that we placed in the vicinity of where we did trials in urban situations. So this is a little town called Riverdale, and we applied pyrethrin plus PBO in August for 2 weeks, and then we applied once, and then we applied preletrin, sumethrin, which is duet, a week later, and then we also applied pyrethrin and malathion 3 times the following month, and only then did we see a reduction. But the problem is, this is October, and we know that mosquitoes are already starting to decline in October. So we didn't compare this to a control site, where a town nearby that was similar, that perhaps we should have done, and it's something that we need to do in the future. But the point here being is that a single application really doesn't have much reduction, cause much reduction in mosquitoes. And maybe you have to apply aerial spraying for 2 or 3 or maybe even 4 consecutive nights or weeks to have any effect. Okay, we like being, what's the relationship between mosquito abundance and disease? We all know that that's, you don't always have disease coincident with high mosquito abundance. So that's a question that we're going to have to try and address further down the line. And I mean, using epidemiological data in this period, there were like, I think 3 people contracted West Nile, and that's not a sample size you can use for any epidemiological investigation.
Anton, what about the type of spraying? So if you spray with a plane or with from a truck,
So all of this is based on truck mounted spraying. None of this is done on aerial stuff,
but
which is
aerial,
what we have to do as
Okay.
well. It has to be something that we follow up with. The idea being that aerial spraying might offer better control, but to get permission to do aerial spraying it's a whole new ballgame regulations, and most districts don't have that capacity. And if a district does, if they do adulticide, most of them adulticide on a very small scale in people's backyards with handheld foggers. And then some districts are prepared to spray from a truck riding up and down the streets in the town. And even then, you know, they have to get prepared for that weeks and weeks in advance. If there's a disease outbreak, then of course it's going to be much easier then to get the regulations and permission to then apply aerial spray. But we haven't had disease outbreaks. So just haven't had that. But there are some districts that do aerial spraying. Sacramento Yellow district, they do aerial spraying. I think you know, they're wetlands. So that would be, I'd have to talk to them and see if we can set up some trials, collaboration with those districts that do aerial spray from the plane.
I just think it would affect the like orchard thing, you know, like because it would come down
Sure.
from the top.
Yeah, one.
Yeah, cool.
But then again, the leaves on the top might capture all the insecticide, and then the ones that are resting in the bottom might. So we'll have to, you know, obviously place sentinel cages at various angles and at various distances within the canopy.
So it seems like the success of this program is about contact between the vector and this poison, which is mediated by airflow, particularly around objects that are in the way. So I'm wondering, on this project, is there any like aerospace engineers or people that study airflow around objects? Because I know that that math is like very sort of predictable, how that works around airflow around objects.
Yeah, I mean, sure, you bring up a good point, and I don't know anybody with
Yeah.
expertise in that field, but that might be, that would be, yeah. But then there's another whole series of variables, and yeah, really makes it complicated.
And most of those insecticides are disintegrated by UV. Have you done any chemical tests to see how they prolong into the nature, like how long they get into disintegration?
I haven't done that, no. But there is an aim within PACWEC. There is, I've forgotten his name, but there is an expert who's looking at the persistence of the pesticides in the environment after the spray. And it would be good for us to collaborate with a person from Riverside. I forgot his name. And then just much the same thing here, where we looked at, so that was in an urban area, and this is now in a rural area, where it was, so we really didn't see much decline in populations after URV spraying. So future challenges, there are many. One of them, of course, relates to understanding a little bit more about the resistance mechanisms of the mosquitoes that we're actually targeting. So is it just Kango, or are there P450s, Yesterases, or even particular reduced penetration? Could there be some behavioral resistance mechanisms that we're unaware of? For instance, some might just have the ability to detect the chemical before others and avoid it before others. So we're not, those are all different mechanisms that we consider. And of course, we really just scratch the surface in understanding resistance mechanisms in mosquitoes. I mean, you can ask Brad there how complex this is. Just even to look at P450s, which are genes that are multifunctional and separating the pre-450 that is involved with the actual detoxification of the chemical versus destroying other parts of the pathway. It's very, very difficult to separate an ion. And we know nothing about behavioral-induced penetration forms of resistance in any of these mosquitoes in California. Behavioral resistance is an important issue in malaria control, where we're now seeing mosquitoes not flying indoors as often in Africa as they were in the past because they're detecting the chemical and just avoiding the house. And they're biting people outdoors more often. So that's an important form of resistance that need to be considered in malaria control. And then reduced penetration. You do see this in acar, in ticks, where the cuticle is, the structure of the cuticle is slightly different, so it's harder for the chemical to get into the organism in the first place to reach its target. And this is the other aspect that concerns me a lot, which we have to try and iron out. And that is, even if we supposedly are dealing with a population that we thought were quite uniform with respect to the KDR allele that confers resistance, you still see tremendous variability in terms of the knockdown responses. So even individuals that are susceptible for the KDR gene, some of them are surviving up to 2 hours, 3 hours in the bottle. You always have these outliers, and it kind of suggests that there must be other resistance mechanisms that are involved. So even just correlating KDR frequency with what we see in the bottle bioassay is not, it's not entirely coincident. And that's why Donnelly mentioned in 2009 the KDR genotype might explain only a portion of the heritable variation in resistance, and that diagnostic assays to test importance of other resistance mechanisms in field populations are required to be done in unison with the bottom line assays. And then there was work that was done by Zhu in 2006 who showed that while a particular genome, KDR allele, was not associated with resistance phenotype, different level expressions of these alleles showed association with resistance. Here we're only looking at the genotype. We're not looking at expression. And so individuals that are heterozygote may very well just be, might very well be just expressing the susceptible allele. That's why most of them get knocked down earlier in the bottle than later. But once again, see these outliers. So it's a difficult question between genotype and phenotype, expression of proteins that we need to take into consideration. So there's 4 years of hard work ahead of us. And there's multiple insecticides and formulations that need to be evaluated. We've just had deltamethrin, which is known as DeltaGuard, we've now approved for use in California. So I'm going to have to work with Dennis Candido and hopefully do some trials with deltamethrin, which seems to be the pyrethroid that Aedes aegypti and Culex propens complex are most susceptible to in terms of the pyrethroid family of chemicals. There's multiple mosquito species that we have to consider. The CDC is not just interested in Aedes aegypti, they're interested in other mosquito species. And I put in Aedes notuscriptus here because I just came back from Greater LA and Susan Kluge revealed that notuscriptus, which is used in Australia, which is this mosquito here that looks a bit like Aedes aegypti, are just blossoming in Greater LA area. They're spreading everywhere. So we now have another invasive species that's doing very well in California.
Where are they from?
And notuscriptus is a very efficient vector of dog heartworm. And the vets in the Greater LA area are reporting just a huge increase in dog heartworm cases.
Where did they come from originally?
Australia. Yeah, and so they're also reported to be minor vectors of Ross River virus and Murray Valley fever. So another invasive species that we have to consider. Then there's multiple environments which do these evaluations, open versus urban and agricultural settings. Then coming back to your question, there's handheld applications, there's truck mounted, and then of course there's from airplane applications. And of course, there are multiple methods that we can use in the evaluation of these URV trials. You know, we can fiddle around with the design of the sentinel cage, we can fiddle around with the design of the spinners that capture the droplets, chemicals, and different, well, as I said, different environments. So there's a tremendous number of variations that we need to look at. But this is a question I've been asking a long time. You know, why am I doing these assays? I can't advise the district for it. So finally, we have some money to try and address this issue. And this pathway grant obviously provides us with opportunity here for us to cross-collaborate between different units. Because I produce bioassay data, which I just keep in the lab. I think it's a perfect opportunity for us to start sharing data, set up a database where different districts that are doing bioassays can put the data into the, maybe use CalServe as a database for us to put all this data. The Department of Public Health, they do KDR phenotype testing. And so can we relate what they do to what I do in the lab for bioassays? So there's plenty of opportunity for cross-collaborative opportunities here. So with that, maybe it's time for one or two questions. Yeah.